Hello, my name is Fran Hoffart. I'm an application engineer in the power group at Linear Technology. Today I will be talking about a linear technology product designed for energy harvesting. Energy harvesting is the process of extracting energy from the surrounding ambient and converting it into a usable form. But with most energy harvesting methods, this energy is not available 100% of the time. Thus, it requires some method of energy storage, usually a rechargeable battery. Linear Technology has a number of products optimized for harvesting electrical energy that include the LTC 3108, 3109, LTC 3588, and the LTC 3105, which I will be focusing on today. But before I start on the LTC 3105, I want to talk briefly about an abundant source of energy that is all around us, and that is solar energy. In addition, since the input power source for the circuit I will be describing are solar cells, I will cover a few solar cell characteristics and how the LTC 3105 maximizes their output power. Solar energy is an unlimited source of power generating about 1,000 watts per square meter in full sunlight. Generating power using solar cells is very popular because of their ability to generate voltage directly from sunlight, although additional circuitry is needed to extract the maximum power from the cell and to control the storage of this power. A solar panel consists of individual solar cells connected in series or a combination of series and parallel configurations. Solar panels are specified in watts of output power. Each cell in the panel produces an open circuit voltage of approximately 550 millivolts at 25 degrees C, dropping to 500 millivolts at 45 degrees C, and dropping further under load. Maximum output current is specified as short circuit current and is dependent on the physical size of the cell, the type of cell, and the amount of sunlight hitting the cell. This first graph shows the slowly drop in output voltage of two series connected solar cells in full sunlight as the load current is increased over a 5-second time period. As the current approaches the cell's maximum output current or short circuit current, the cell voltage begins dropping much faster. When the load current equals the cell's maximum output current, the cell voltage drops to near zero. Note that on the left side of the graph, we have voltage but no current, zero power out. On the right side, we have current but very little voltage, also near zero power out. Somewhere in between these two extremes, there's a solar panel voltage and current where the panel is producing peak output power. Although present solar cells are relatively inefficient, ranging from 6 to 15%, there is a narrow range of voltage and current where the solar cell delivers maximum output power. This next graph shows the solar panel's output voltage and current with an added output power curve. This curve clearly shows the solar panel output voltage that delivers a maximum output power. By maintaining the panel's output voltage between 700 and 800 millivolts, the maximum power can be extracted from the solar panel. This is the theory behind the maximum power point control used in the LTC 3105. The LTC 3105 is a step-up DC to DC converter utilizing maximum power point control. This converter is designed primarily for producing electrical power from ambient energy sources, such as low-voltage solar cells and thermoelectric generators. Other impressive features include synchronous 400 milliamp switches with output disconnect, low 250 millivolt startup voltage, which allows the converter to operate from a single solar cell, a 6 milliamp low dropout regulator, power good output, burst mode operation, and the output voltage can be above or below the input. All this in a 10-pin 3x3 millimeter DFN package or a 12-pin MSOP package. The circuit shown here uses the LTC 3105 boost converter powered by a 2-cell solar panel to charge a lithium-ion battery. Also included in the circuit is an LTC 4070 shunt battery charger to limit the float voltage on the battery and to indicate when the battery is fully charged. A 75K resistor sets the LTC 3105 maximum power point to approximately 750 millivolts. Input power is absolutely necessary when a solar panel supplies input power to a DC to DC converter, as the following curves will show. The graph on the left shows the output voltage and current for a 2-cell solar panel as the sunlight intensity changes from 100% down to 20%, then back up to 100%. This could be similar to a cloud passing overhead. Also included in this graph is the output current of the LTC3105 that is charging the lithium-ion battery. Note that as the sunlight intensity drops about 10%, the solar panel's output voltage and current also drop. But the LTC3105 maximum power point control prevents the panel's voltage from dropping below the programmed 750 millivolts. It accomplishes this by reducing the LTC3105 output charge current to prevent the solar panel from collapsing to near 0 volts, as shown on the graph on the right. In this graph, the conditions are the same, except the maximum power point control was disabled by shorting the MPPC pin to ground to illustrate the need for maximum power point control. Notice that for a similar 10% drop in sunlight, the panel's output voltage quickly drops to about 200 millivolts, which is below the converter's minimum input voltage, with a resultant drop in output current. Now let's go back to the solar battery charger circuit. The converter's output voltage is programmed for 4.35 volts, although it'll never reach this voltage because of the LTC4070 shunt charger. The converter's output is directly connected to the battery and the LTC4070 charger. The shunt charger clamps the converter's output voltage to one of 3 pin selectable 1% voltages, 4 volts, 4.1, or 4.2 volts, to avoid overcharging the battery. The LDO regulator is set to 2.2 volts by grounding the FB LDO pin. Other LDO voltages can be obtained using feedback resistors. In this circuit, the LDO output is only used to drive the status LED. This assures that the LED is off when there is no input power. The solar panel used in this example provided over 60 milliamps of charge current under direct sunlight, dropping to about 16 milliamps for 20% sunlight. Other charger features include provisions for sensing battery temperature using an NTC thermistor. This reduces the battery float voltage at higher temperatures and also includes an active output to indicate when the battery is within 40 millivolts of the float voltage or nearly charged, and a low battery output that drives a MOSFET to disconnect the load, thus preventing deeply discharging the lithium-ion battery. In conclusion, the LTC3105 has unique features that make it ideal for low-power solar applications. Maximum power point control allows the converter to extract the maximum available power under varying sunlight conditions, while the LTC4070 provides the precision float voltage required for lithium-ion batteries and additional battery functions. Visit us at www.linear.com for more information. Thank you.